So today we are going to Unit 10, okay? So Unit 10 is about logistic regression. And any one of you ever done logistic regression before? No? Some of you, only one of you. Okay. But you do know what is linear regression, right? Last week we introduced linear regression, and that's for estimating the numeric variable, okay? The target variable is a numeric variable, so we are actually predicting kind of like this, right? We are kind of predicting a variable y by a linear combination of x, okay? By linear combination, we mean that we have a series of x, and then every x is multiplied by a coefficient, and we add them together and use this linear combination to predict the value of y, right? That's linear regression, okay? So today we are going to do a logistic regression. So logistic regression is to predict not the value, but the event probability, right? You are predicting something would occur, something would happen or not, okay? So if it happened, it's 1. If they are not happen, it's 0, okay? So the target variable is not the value, okay? The target variable is a kind of like an event. For example, whether a customer will buy it in the next month, right? So he will either buy or not buy, right? So it's kind of like 1, 0. Whether you will have a heart attack, whether this patient would have a heart attack in the next year, right? So that it would either happen or not happen. So the target variable is kind of like a binary variable. It's like 1, 0, 1, 0, right? And when we are predicting this event, we are not predicting the target variable itself, okay? The model is would kind of predict the probability of the event, right? For example, for a customer, we are predicting for each of this customer, for each of this individual customer, the probability that her would come to our store and buy, right? We are predicting the probability, right, that he will buy. We're predicting the probability that this patient will have a heart attack, right? We are predicting the kind of like event occur or not, right? So the target variable is kind of like a binary variable, and our model is predicting the probability that y equal to 1, okay? The target variable is the 1, 0 type of binary variable, and we are predicting the probability that y equal to 1, okay? That is what logistic regression is used, okay? And actually in the business environment, we can say that the logistic regression is used very, very often in the business scenario, okay? I believe that it's more useful in the business scenario than that. Okay. So okay. So in business, actually, I think that the logistic regression is used more often than the linear regression. Okay. So today, this is what we are going to do. Actually, first of all, we would introduce what is logistic regression, right? First of all, is mathematical form, okay? It's a little bit complicated, but don't worry too much. That's you don't really need to, right, remember that mathematical formation formula, because the R package will take care of them for you, right? You just know how to do a function code to build a model, okay? And then how to use this model to do the prediction, okay? And also, as I told you that this linear regression, the coefficient has some implication about the relationship between x and y. In linear regression, this coefficient actually imply or estimate the marginal effect of x toward y, right? Because if y is estimated by b1 plus x1, right? So when x1 is increased by 1, when x1 is increased by 1, the y hat is incremented by b1, right? Okay? So the coefficient in linear regression or logistic regression, actually logistic regression is a kind of linear regression, as we will see, as we will explain later, right? It's still a kind of linear regression. So it still uses the linear combination of x to predict y, but it is not predict the y itself. It predicts the probability of y equal to 1, right? So that is the difference. But it still use this linear combination type of thing. So its coefficient also have some implication about the relationship about x and y, okay? But it's a little bit more complicated, okay? Okay, so after we interpret the coefficient, another important thing is to measure the model accuracy, right? Okay, so again, this is what is more complicated than what we do in the linear regression. Okay, so we will use a couple of a couple of notebook to explain what is logistic regression, to explain how to build a logistic regression model and how to use that model to do prediction. And we will do some explanation on how to interpret its coefficient, right? And then we will talk about the accuracy measurement of logistic regression. Okay? So this is, I believe, for next week, right? After we get familiar with logistic regression, the next thing is to use the prediction to do decision, right? We are using model to do prediction, right? But prediction is not our final purpose, right? After you do the prediction, you want to take some action, right? For example, you know that this patient has like 50% of probability that you would have diabetes. Okay, so what do you want to do with her, right? Do with this patient, right? For example, you know that this customer, the buying probability of this customer is like only 5%, right? So you might want to do something to pull him up, right? Okay, so after we know the buying probability and also the estimated buying amount of our customer, right? We know its future buying behavior, then we can actually like design some instrument and trying to improve his or her buying behavior, right? That's what we're going to do. Okay? So, but that is for next week. Okay? This week we will concentrate on this logistic regression. Okay? And again, our this week our material is here, right? You go to the unit web page, and here you can actually see that we have two files again, right? So this is the PowerPoint file that I'm using, and this is the zip file, right? So download the zip file into your code directory and unzip the file, and you will see a folder called 10_logistic regression, right? And under this, here we will see C3 notebook, okay? And that's the notebook we are using today, okay? Okay, let's explain what is logistic regression with our notebook first. Okay. Let's see. I actually should pull it forward so it's easier. Okay. Logistic regression model. Okay. So the different as I say that last week we are talking about linear regression model, so we are using this kind of like linear combination, right, to estimate the value of y, right? And for logistic regression, it's not the same, right? Again, we are still using this linear combination of x, but the value of this linear combination do not predict y itself. And the purpose of us is to predict the probability of y equal to 1. Okay, but there are some mathematical complications here. Okay, the linear combination is actually predict the log of y equal to 1. I'll explain what is log, right? Okay, so it's actually the log R of y equal to 1. Okay, so the linear combination of x, we were sometimes express it by f of x, right? Okay. So this value is equal to the log of y equal to 1. Okay, and actually we can transfer the log into probability by using logistic function. Okay, and that's why we call this regression or logistic regression. Okay, again, I say it again, right? Right now in logistic regression, we are using the linear combination of x, okay, to predict the log of y equal to 1. Okay, and we can transfer the log into probability by logistic regression. Okay, so that's why we call it logistic regression. Okay, because we are transferring the value of linear regression, okay, with this logistic function in order to estimate the probability of y equal to 1. Okay? Let me do some more explanation about what is log and what is R. Okay? So that's the page here. Say that. Put it forward. Okay, so usually we are talking about probability, right, of y equal to 1. It's by now you should already learn what is probability, right? Okay, it's clear. But there's another way to measure probability. Is called R. Okay, it is actually P divided by 1 minus P. Okay, very straightforward, right? So for example, if I have an event that the probability is 0.9, okay? So here the P is equal to 0.9 and 1 minus P will become 0.1, right? So R has become 9, okay? So this is often used in gambling, right? Okay. For example, if you have a match, right? A soccer ball match, for example, there are team X, team Y, right? So, and the team A, the first team, they have a winning probability of 0.9, and the other team, of course, it has a winning probability of 0.1, right? So the odds of team 1 will win is actually 9. Okay, so odds is actually the ratio of two probability. Okay, so let's have some practice. If the P equal to 0.99, right? So what is the R? If it is 0.99, then 1 minus P would become 0.01, right? So what is R? How many? 99, right? So if the probability of P is 0.9999, what is the R? It is 9999, right? So if something, the probability is kind of like very low, for example, you buy a lottery, right? You buy a lottery ticket, the winning probability is actually very, very low, right? Isn't it? Right? So the opposite is you will not win. The probability is you will lose. The probability is very high, right? Okay. So sometimes this is actually the art is actually if the game is fair, okay, is the money that the house should pay you, okay, if you win, right? Okay. If you bet on something that probability is very, very low, you will get a very, very high multiply. You will win a very large prize, isn't it? Right? So art is actually has a 1-to-1 and monotonic and nonlinear transformation to P. P. What is the range of probability? I mean, the range of probability, what is the range? It's very narrow, right? The smallest probability, what? The smallest probability cannot be negative, right? It must be a number between 0 and 1, right? Okay, but art is different, right? It is actually it can be like as we have calculated, it can be very, very large, right? Theoretically, it can come to infinity, isn't it? Right? So, as I explained to you, when you are buying a lottery ticket, when the when the probability to win is like just maybe 100 million to 1, right? Okay, so that odds could be very, very large, right? Okay, so that is the another thing that we as I say that odds is another way to represent P, to represent probability. Okay, and if we take a log, a natural log on odds, we will call it log it. Okay, so basically probability, odds, and log it, they are kind of like a trinity. They are talking about the same thing, right? Okay, they are talking about probability, but they are different unit, different way to represent probability. Okay, P is probability as we know, and odds is P divided by 1 minus P. And log it is actually you take a log transformation to odds. We call it log it. But why do we want to? Why bother that we like? They are all talking about probability, right? So why bother doing this transformation? It is because that when we are talking about logistic regression, okay, we actually this linear combination is actually the log it of y equal to 1 instead of probability y equal to 1. When we define this thing, it would make it easier when we do the explanation, when we are doing the explanation of logistic regression. Okay, so log it, you just need to remember that odds is like P divided by 1 minus P, and log it is actually the log transformation of odds. Okay, so these things actually have one-to-one and monotonic and nonlinear transformation. Okay, the range of odds, the range of P is actually 0 to 1, right? But the range of odds can be from 1 to infinity. Okay, it can be very, very large. And when you take a log on odds, the value will become from the negative infinity to the positive infinity, right? Because if the odds equal to 0, the log it would like approaching, when the odds approaching 0, log it would approaching in negative infinity, right? And when the odds approaching positive infinity, the log it would also approach infinity. Okay, so there are 3 ways. Okay, before we going forward, just remember that odds, log it, and probability, they are just 3 different ways in calculating probability. Okay, and the transformation is quite easy actually, and they have a one-to-one mapping. And so monotonic, it means that when probability is large, odds is larger, and log it is larger. Okay, but their transformation are nonlinear. Okay, they are one-to-one transformation. Okay, which means that different probability will lead to different odds, will lead to different log it. Okay, and when P is larger, when one of them is larger, the other two is actually larger. It's called monotonic, because this curve is always going up, right? It never go down. Okay, and then nonlinear means that the transformation is not like a gram, milligram to kilogram. It's not like that, right? It's not like ounce and It's not like pound and ounce, right? It's a nonlinear transformation, okay? And when you have a logit, right? As I told you that in logistic regression, this linear regression, this linear combination would use to estimate the logit of y equal to 1. So when you have the logit of y equal to 1, you kind of use this mathematical form to transfer it back to probability, okay? And this functional form is called logistic function. Okay? Got it? Okay, so this is kind of abstract and some of and kind of there are some mathematical complexity. Okay, so let's take a look at the notebook and give you some real example in what is logistic regression. Okay. Now let's take a look at 10A first. Okay. And again, let's execute the first blocks, and then maybe the second block. And in the subblock, we will load a data set into here, and then we name this data frame called D, and within D, I only have a Y and 2 X, okay, X1 and X2, to make it simple, right? So I rename the probability to so that it is easier to explain this mathematical relationship. Okay, so this example data frame, in this example data frame, we have a target variable Y, and we have 2 predicting variable X1 and X2. And if you take a look at Y, you will see that the value of Y is either 0 or 1. Okay, you see that? Okay, so Y is yeah, it's integer, but it only has 2 values, 0 or 1. Okay, as I told you, the logistic regression is to predict the event occurrence, right? So this event would either occur or not occur, right? So it's only have the target value of the actual value of Y is actually just 1 or 0, just 1. Okay, and we are using the linear combination of X1 and X2 to predict not the value of Y, but the probability of Y equal to 1. Okay, that is what we are going to do in logistic regression. Okay, so let's see how we do it. Okay, in R, actually, let's take a look at the notebook. I believe it is easier. Okay, so as I explained it here, right? The model that actually categorical model, sometimes we call it classifier. Okay, if your target variable is a categorical outcomes, and then you cannot use linear regression to do the prediction model, right? Predictive model. You have to use a classifier to do the prediction. Okay, and logistic regression is the simplest classifier method that only predict binary outcomes. Okay, so it only predict like categorical variable or 2 outcome. Okay, it cannot predict an outcome of more than 3 possibilities. Okay, so it only predicts the binary outcomes 0 and 1. Okay, and it actually predicts the probability of y equal to 1 because the outcome variable can only be 0 or 1, right? As we see here. Right? So we have this simple example. As we see it, we have 131 data point, and here the y variable only equal to only equal to 1 or 0, right? We can do a we can do a table to see. As you can see that in this 131 point, we have 33 1 and 98 0, right? Okay, so that's usually before we do when we have a binary target variable, the first thing we do is we want to see the base probability, right? It's about 1/4 of 1 and 1/3 of 0, right? So we just have some basic idea. Just this thing is like it's like when the y is a numeric variable, you want to see its average, right? Okay, and when the y is like binary, you actually want to see the base probability. Okay, actually, if you do an average on y, you will see that let's skip this. So you can see that it is the probability of y equal to 1, right? If you randomly select one point out of this 131, right? The base probability is kind of like 0.25, isn't it? Okay, and that is simply this base probability can be acquired simply by doing average on y, right? Okay, so these two things are kind of like this is very similar to what we do in linear regression when we like want to see the y bar, right? The average of y. Okay, and this is the same thing when we do a y bar here. We are actually not getting the average value of y, and because that y is binary, so this average also implied the probability of y equal to 1 when we randomly draw a point out of this sample, right? Okay, so that is the basic probability. The thing that before we do the model, before we have a model, we actually have some basic idea about what is the probability of y, right? If we do not have x, if you only have y, and then this 0.25 is the best guess of y equal to 1, right? If you randomly select a point out of this sample, isn't it? Okay? If you do not do model, right? Without the model, then you can still estimate y. You can still predict y by its average, isn't it? Right? That is the idea without model. But with model, we will have a better prediction, right? Isn't it? Okay? Just like what we did in linear regression. Okay? So the same concept apply to logistic regression. Okay? Now, Now, now that we not only have y, we also have x, right? So we can use x, the linear combination, to predict y, and usually you have a better, if x and y have some relationship between them, usually we will have a better accuracy of prediction, right? And the way to do a linear regression is a little bit different. It's similar but different from linear regression. In linear regression, we call a function called LM, right? Still remember it, right? But now for logistic regression, we need to call GLM, okay? The G is general linear regression model, okay? Actually, the GLM can build not just logistic regression. It can build Poisson regression model. It can build negative binomial regression model. It can build a series of model by using different transform function, right? Okay, and when the transfer function is logistic function, we will call it like logistic regression. Okay, so it's called generalized linear model, and with this generalized linear model, the linear regression do not predict y directly. It need to go through a transfer function to predict y. Okay, so and because it can use different transfer function, so it can actually use to build a family of model, not just logistic regression. Okay, and because it can because this GRM can predict a family of different model, so you will need to specify which member of the memory you want to build. And in the case of logistic regression, you need to specify family equal to binomial. Okay. Okay. So to build linear, logistic regression, again you need a formula to specify your target and predicting variable. Okay. Separate by tilde. And then you need to give the data frame, of course. Okay. And if you want to build a logistic regression, you always have to put the family equal to binomial. Okay. And you call the GRM function, and then you get the model. You can name the model whatever name. You can give it the name that you choose. Okay. And then again, if we want to see the coefficient, we can call the summary function on this model, and here we will have the coefficient estimation. Okay, and so another way to get this coefficient is you simply call this coefficient function on this model, and you will get the B0, B1, and B2. In this case, we only have two predicting variable, right? So we will have three coefficients. Remember that, right? Because this linear regression, in addition to the coefficient associated with every predicting variable, there's an intercept, right? Remember that, right? Okay. So we have B0, B1, and B2. Okay, and when you build the logistic regression, again the method, the GRM method, will create a model. And when they create the model, it would choose a set of coefficients so that the error between the actual y and the predicted y are lowest, are smallest. Okay, right? Okay, so the methods actually choose this coefficient so that you can predict variable y by this linear combination. And in the case of logistic regression, you need to do some transformation, right? Okay. So as we say that it do not predict y directly, it actually predicts the log of y equal to 1, okay? And actually, if you do some transformation, you can transform the this linear combination into the probability of y equal to 1, okay? And this is how we do it in R, okay? It's kind of quite straightforward, right? This is the linear, because B is actually this vector, right? B is actually B0, B1, B2, and if x1 equal to 3, x2 equal to 4, right? Okay, so B0 is actually multiplied by 1, and B1 actually multiplied by okay, B1 is multiplied by how many? 3, right? So x1 is 3, x2 is 4, so B2 is multiplied by 4. So this linear combination is the log of y equal to 1, right? And because log is the log of R, so if we do a exponential transformation on log we will get the R, okay? And with this formula, we can transform R back to probability, right? So if you want to do it, if you want to, given the coefficient, you can actually transfer the log back to probability in this way in R, okay? But actually, you don't really need to do that, okay? You can simply call the predict function as we will explain later in the next hour, okay? So as you can see that if it's 3, 4 and use this same thing, you can calculate the log R and probability, okay? If it's 2 and 3, you simply change it as 2 and 3, and the rest of the thing, the rest of the code are exactly the same as this one, right? Okay? So there are very straightforward transformation, although that this do not predict the probability of y equal to 1 directly. The transformation is kind of like straightforward, okay? You can do it simply by a few lines of code, okay? Okay, so this is already 10 o'clock. Let's have a 10 minutes break, and we'll be back at 10 after 10, okay?